Dear Stefan, thank you very much for your kind introduction. Good day to everyone, wherever you are, and thank you for having me. Many of you know OPC UA from industrial automation, but today we'll shift focus to the laboratory and analytical domain. Unlike industrial automation, the outcome of laboratory and analytical processes isn't typically a physical product, it's data. That's why seamless integration between data generation, documentation, and processing is so essential. To highlight how communication and data standards come together, I'll briefly introduce Let's OPC UA, the new companion specification for lab analytical devices, and show how it integrates with Allotrope Foundation technologies, enabling a harmonized, interoperable data layer that spans the full data lifecycle, from sample preparation and measurement to documentation and further processing. Let's take a look. Let's start with a quick look at Let's OPC UA, the companion specification for laboratory and analytical devices. It's an official OPC UA companion specification released in December 2023. Let's addresses the most important use cases of the laboratory and analytical domain. Basic operation, such as reading sensor values and controlling device states. Orchestration, which includes program management, starting monitoring and stopping predefined workflows. Results management, exposing resulta in a structured, traceable way. And asset management, covering metadata, identification and lifecycle aspects. Let's builds directly on well-established companion specifications. Devices, the foundation of every device-specific companion specification. Machinery basics, enabling Industry 4.0 compliant integration. And asset management basics, to align with broader OPC UA asset strategies. So, Let's doesn't reinvent the wheel, it extends proven OPC UA models to fit the specific requirements of the lab and analytical world. This slide shows the wide range of laboratory and analytical device types we've successfully modeled using Let's OPC UA. It starts with simple instruments like magnetic stirrers, balancers, and pH meters, and moves up to more complex systems such as bioprocess controllers, liquid handling workstations, and even high-end analytical platforms like HPLCs. Despite the variety in function and complexity, all these devices can be modeled using the same set of Let's OPC UA information model types. From the most basic to the most sophisticated device, Let's enables a consistent digital representation, enabling plug-and-play automation, orchestration, and seamless data integration. Let's take a step back and look at the outcome of different types of processes. In industrial manufacturing, the result is something tangible, a part, a component, or even a complete car. In energy systems, the outcome is clear. Electricity, heat, or power, something you can measure and consume. Now, compare this to the laboratory and analytical domain. Here, the result is typically not a physical product, it's data, measured, interpreted, and often manually documented. And ideally, that product isn't just any data, it's fair data. This shift from physical output to information output is key to understanding the growing importance of lab data standards like Let's OPC UA and Allotrope Foundation technology. But what exactly do we mean by fair? Fair data isn't just a buzzword. It's becoming a core requirement across all lab domains. In academia, FAIR principles support transparent and reproducible research. In chemical and pharmaceutical R&D and quality control, they ensure reproducibility and enable data reuse across teams, sites, and systems. And in regulated environments like GMP and GLP labs, FAIR data is key to ensuring compliance, auditability, and long-term traceability. So what does FAIR actually stand for? Findable, accessible, interoperable, and reusable. Together, these principles support not only data quality, but also data integrity, both of which are now expected in any digital lab environment. Let me briefly introduce the Allotrope Foundation, a cross-industry consortium that has been pioneering cutting-edge data standards for fair laboratory data. On the left, you see a selection of its members and contributors, including major pharmaceutical and chemical companies like Amgen, Bayer, BASF, Boehringer Ingelheim, Genentech, GSK, J&J, Merck, and many more. You'll also find leading instrument and platform providers such as Agilent, Bio-Rad, Shimadzu, Thermo Fisher Scientific, and Waters, as well as digital ecosystem players like Benchling, BioVia, and others. And importantly, a broad range of academic institutions also participate in this initiative. So what does this show? Allotrope is widely supported across industries, from instrument vendors to data platforms, end users, and scientific institutions. On the right, you see the key components of the Allotrope Foundation technologies. AFO, the Allotrope Foundation Ontology, ADM, formal data models for specific scientific processes, ADF, a container-based file format, and ASM, the Allotrope Simplified Model. For this presentation, I'll focus on the two technologies most relevant for integration with LAD's OPC UA and the implementation of FAIR lab data, AFO and ASM. Let's now take a closer look at the Allotrope Foundation Ontology, or AFO. Put simply, an ontology defines what things mean and how they relate to each other. In the lab context, this means giving shared meaning to concepts like instruments, samples, methods, and results. AFO is a domain-specific ontology built for the laboratory analytical world. It provides a structured, shared vocabulary that enables consistent and machine-readable representation of data. AFO is built on W3C semantic web standards such as RDF and OWL. This means it's not just human-readable but can be understood and processed by machines too. As of today, AFO includes more than 3,500 defined terms, along with their relationships, hierarchies, and contextual links. To summarize, AFO provides the semantic layer that allows devices, systems, and data models to understand each other, making lab data machine-readable, comparable, and fair by design. Let's move on to the Allotrope Simple Model, or ASM. ASM is a JSON-based format for structured laboratory data, designed to be easy to generate, validate, and interpret by both humans and machines. What makes ASM especially powerful is that it enforces both strict syntax, uses JSON schema, which ensures each model follows a defined structure, and strict semantics, because every key in an ASM file is tied directly to a term in the Allotrope Foundation ontology. This ensures not only consistency in structure, but also shared meaning across systems, teams, and organizations. Today, there are already more than 70 ASM models available, covering many of the most common analytical techniques in laboratory environments, such as simple techniques like weighing or viscometry, all the way to complex analytical techniques such as HPLC measurements. ASM delivers fair data by design, structured, meaningful, and ready for integration, right from the moment it's created. To illustrate the need for seamlessly integrated fair data, let's walk through a practical example. the digitalization journey of a viscometry measurement process. In the first step, we connect a legacy viscometer, equipped only with an RS-232 interface, to the OPC UA world using a Let's OPC UA gateway. This already allows the user to monitor and control the device using standard OPC UA tools. They've taken a great first step, automating what used to be a manual process. The user can now access live data, extract results as CSV, and even use that in an Excel sheet for documentation. The feedback is something like, I'm happy, I have automation, I get the data through OPC UA. But they also realize this is not fair data. The file format is proprietary, the meaning of each column isn't explicit, and I still have to rely on Excel to document what was done and how. So, great progress on connectivity, but not yet on data integrity, reusability, or context. Let's continue our viscometry journey. Now, the user has taken another step forward. They've learned about the allotrope technologies. They've even implemented a custom conversion tool which takes the output they receive via Let's OPC UA and transforms it into structured ASM files based on the geometry manifest. That means the result data is fair, it's machine readable, structured and semantically annotated using AFO. Sounds great, right? But the user quickly realizes something's still missing. Sure, the result data is fair, but the system isn't. It's a classic halfway point. Structured documentation, but still lacking semantic continuity from generation to result. So, what exactly is still missing? Well, the result data is fair, but the systems that generate, transfer, document, and process it still speak different languages. Let's take a look at some terms used in Let's OPC UA versus their equivalents in AFO and ASM, such as sample, sample identifier, program template, device method, device template ID, method identifier, result, experiment result, user, analyst, current time, elapsed time, and so on. Technically, they refer to the same concepts, but they are labeled differently, structured differently, and often stored in disconnected systems. And so the user says, I need seamless, fair data, not just fair at the endpoint, but fair from the first byte to the final result. So, what's the vision? What would truly seamless fair data look like? The goal is simple, but powerful. A single fair data representation that remains consistent from data generation and in-process use all the way to documentation and further processing. No remapping, no renaming, no guesswork. Just one shared language used across methods, devices, application software, and result data. And how do we get there? By using the Allotrope Foundation ontology as the common vocabulary between communication standards, like Let's OPC UA, and data standards, like Allotrope Sample Model. The user sees this and says, now this would be fair. It's the digital lab's holy grail. One model, one vocabulary, from sample to insight. Let us begin with the technical foundation for semantic alignment. The Allotrope Foundation ontology terms are converted into a standard OPC UA node set following the specifications of OPC UA Part 19, dictionary references. By loading this node set into the Let's OPC UA server's namespace, we create a machine-readable vocabulary layer directly within the server, where every concept is represented with a defined URI and a UDIM-readable label. This feature was first introduced by the byDr Companion Specification, where it's used to reference terms from the ISC Common Data Dictionary within OPC UA models. So now the Let's server doesn't just expose device data, it also knows how to refer to standard semantics defined by the Allotrope Foundation ontology. This sets the stage for the next step: semantic labeling of the server's objects. In the next step, the server performs a semantic pass over its own namespace. It automatically crawls through the object structure, and for each node defined in the Let's Companion Specification, it attaches Allotrope Foundation ontology terms that represent its real-world meaning. Here's an example. We have an instance named analytical method A of a program template type, which in Let's represents a predefined method or workflow. We now annotate this object with AFO terms like device method and method name. This labeling bridges the gap between device data and semantic context automatically and consistently. Now, while Let's already provides a generic semantic model, real-world devices often have specific roles in a laboratory analytical workflow. So we go one step further. In the example, we enrich the object with additional application-specific AFO terms, such as measurement method, rheometry, and viscosity. Why? Because this program template describes a specific analytical task, measuring the rheological property named viscosity. This final layer of semantic labeling makes the system fully interpretable for machines, data models, and downstream processes like AI-based reasoning. It's where plug and play meets deep domain knowledge. Now that the semantic labeling is in place, we can see the impact in action. Instead of a generic OPC UA browser, we are using a purpose-built Python-based Let's OPC UA browser. This browser understands OPC UA, of course, the Let's Companion Specification, and the Allotrope Foundation ontologies. By the way, both this browser and the simulated viscometer server will be published as open source on GitHub today. In this view, we are looking at the Program Management tab, which follows Let's domain use cases. On the left, we see a list of available program templates, including our earlier example, analytical method A. The center area is used to initiate and monitor program runs. This is typically how an LES or LIMS system would orchestrate workflows. On the right, we see result entries, structured and semantically traceable. You may have noticed the question mark icons throughout the UI. Clicking them opens up the semantic definitions of each object based on Allotrope Foundation ontologies. In this example, we've opened the full FO definition of the program template, and we see exactly what this object represents. A viscosity measurement using a defined analytical method. No ambiguity, no guesswork. Now, let's switch to the Operation tab, the part of the UI used for live interaction with the device. On the left, we see a list of measurement and control functions provided by the instrument. For example, shear rate, shear stress, speed control, temperature control, torque measurement, viscosity calculation, and so on. And again, whenever an item has a question mark icon, the browser retrieves and displays the corresponding Allotrope Foundation ontology-based semantic definition when clicked. What's important to note is, this browser doesn't know what viscosity is or how a rheometer works. It just understands OPC UA, Let's, and how to follow semantic links to Allotrope Foundation ontologies. That's semantic plug and play in action. That's real-time monitoring, semantically contextualized and fully machine readable. And just to reiterate, both the browser and the simulated server you see here will be published today as open source on GitHub. Let's now look at one of the biggest benefits this integration brings. We are back on the Program Management tab, but this time we are focusing on the right-hand side where the results of the last program run are displayed. Here we don't just see raw numbers. Instead, we get full contextualized information. Which exact sample was analyzed, utilizing which method, when and by whom, and so on. All of this semantically enriched, labeled with Allotrope Foundation ontology terms wherever applicable. Below that, we see the analytical endpoints provided as OPC variables inside the result data, again labeled with Allotrope Foundation ontology semantics for clarity and machine readability. But most importantly, the complete result is also available as an allotrope simple model, following the geometry manifest. It's embedded directly in the OPC UA server in two ways. One, as an OPC variable named ASM containing the full ASM.json result, and as a downloadable file provided via OPC UA's standards file type mechanism in the file set. Everything is interconnected through Allotrope Foundation ontologies labeling, creating a single, coherent, machine-readable data infrastructure. That is what we mean when we say fair by design. And by the way, in the next presentation, my colleague Heiko Fessenmeier from Agilent will introduce a third, very elegant approach for representing Allotrope simple model data in OPC UA. So stay tuned. Let's take a step back and look at what we've actually achieved. We set out on a journey to solve a long-standing challenge in the lab. How do we make fair data not just possible, but seamlessly interoperable throughout all systems involved? And here's the result. A single fair data representation that stays consistent from the moment it's generated on the device, through in-process use, all the way to documentation, data processing, and even data exchange. This is no longer about stitching things together afterward. It's fair by design. And how did we get there? We started by using the Allotrope Foundation ontologies as our shared vocabulary. We labeled the nodes in the Let's OPC UA server with these terms. And the result data, stored as ASM, uses the exact same terms, the same language to describe what happened. It's a complete integration of device-level communication and high-level data modeling, bound by a shared semantic foundation. In short, we found it the holy grail of fair lab data, and it's real, working, and available today. Thank you very much. That's the real takeaway. A full, end-to-end fair data infrastructure built on open standards, ready to build the connected digital lab together. Stefan, back to you. I'm happy to take any questions.